Looking up to the stars on a bitingly clear night, a horizon away from the nearest town, you'll feel alone. But as your eyes adjust, you are embraced by the light of an entire universe. Surrounded by such scale and wonder, it's hard in that moment to imagine that we are it, isn't it? That we are the only life the universe will ever know, confined as we are on this pale blue dot. Perhaps we are alone. Or maybe, just maybe, given enough time, nature's laws conspire to make life not just probable, but inevitable. I'm Alex McColgan, and you're watching Astrum. Join me today as we explore the chaotic transition from chemistry to biology on our planet, seeking answers to some of the most debated and fervent questions in science. What is life? How could life have emerged on Earth in an environment that would kill us as we are today? And can it begin all over again elsewhere in the universe, or even on our own planet? To begin to answer those questions, let's imagine that while walking across a barren desert, your foot kicks a stone. It wouldn't occur to you that someone put it there or crafted it, since the stone is too simple an object. Now, imagine instead that you stumble across a glistening, precision-made, embossed gold pocket watch. William Paley argued that because, unlike a stone, a watch obviously requires a designer, you'd have to assume that someone had made the watch and placed it there. And because, when you truly think about it, life is far more intricate than a watch, life too must require a designer. It's a compelling argument, isn't it? Even the simplest forms of life are far, far more intricate than a watch, and if a watch requires a designer, surely so must life. Unfortunately, the argument doesn't quite work. But why? What really is the difference between a man-made machine and mankind? Charles Darwin's work on evolution and the origin of species crystallized the idea that life evolves and that all life began from one common ancestor. Therefore, I should infer from analogy that probably all the organic beings which ever have lived on this earth have descended from some one primordial form into which life was first breathed. And there it is, emergence, life from chemistry, something different than the sum of its parts. Darwin understood that life needs no designer. It is able to be more intricate than a watch without a designer because it is a complex, adaptive system driven by natural selection. It has the ability to evolve. A watch is merely complicated. But before we go back 4 billion years to uncover life's genesis on Earth, we should probably all agree on what it is we're looking for. What do you think defines life? What makes something alive? If you're struggling for an answer, don't worry. Even NASA can't get 3 words into their definition without being challenged. This is science at the bleeding edge. NASA defines life as a self-sustaining chemical system capable of Darwinian evolution. Prominent scientists argue that life is not strictly self-sustaining. Life requires an environment with which it has a dynamic relationship, where life draws its energy and raw materials and expels its waste. An environment that is full of free energy, an environment that sustains life. Life's relationship with its environment is crucial to understanding how life is possible. You see, life is, at first glance, in defiance of the second law of thermodynamics. How does the beautiful design of a bacterial cell, with its incredible complexity, control, and order, seemingly defy entropy and emerge out of a structureless chemical soup? According to the second law, entropy should always increase, and systems should get more disordered with time, not less. It was Erwin Schrödinger who realized that it is the environment that picks up the thermodynamic cost in his book, What is Life, in 1944. On closer inspection, when we include the environment that sustains life, entropy does increase overall. The second law of thermodynamics is not broken. In fact, entropy increases faster with life than without. It is this that led Jeremy England, a professor at MIT, to say, You start with a random clump of atoms, and if you shine a light on it for long enough, it should not be so surprising that you get a plant. Life is incredibly effective at transforming energy and increasing entropy. How effective? Let's compare it to the brightest and most powerful object in the solar system, the Sun. In just 58 microseconds, it produces more energy than our species has in its entire history. Pound for pound, though, humans output a staggering 6,000 times more power at rest than the Sun. Despite creating extremely localized order, life degrades free energy to heat, increasing entropy in the universe overall. Unsurprisingly, given that you're watching this video, it's clear that entropy allows for, or even encourages, the development of life. So how did the building blocks of life seemingly defy entropy in constructing order from chaos? How does a living cell build up that can power itself, encode itself with DNA, construct itself too, and have the ability to evolve? And how can it do it all piece by piece while being functional at every step, even though each part is essential? How on earth could life emerge? Well, there is little consensus on the precise way that life actually emerged on Earth, but let's explore the molecules that, without exception, build every single life form on Earth. Perhaps life offers clues to its own origin. The key basic building blocks life uses today, in no particular order, are fatty acids, amino acids, and nucleotides. And all three are believed to have been present on the early Earth, and have even been found on asteroids in our solar system. The first are fatty acids, and despite having little chemical functionality, they create structure and have an extraordinary function built in. These long chain molecules make up cell walls of all life on Earth and are believed to have made the first membranes of protocells. Membranes are barriers and fundamental to create an individual unit. After all, you can't have a house without walls or a country without borders. That's not a political statement. Remarkably, cell-like structures made from fatty acids form spontaneously in water. As anyone who's failed to make a simple mayonnaise will know all too well, oil and water don't like to mix. These fatty acids, with a water-loving head and a water-hating tail, will spontaneously arrange to minimize water's contact with the tail and maximize it with the head. These simple pressures can create a bilayer membrane with a cavity for an early cell to call home. This is called a liposome. Unbelievably, these liposomes can also spontaneously divide and speed up chemical reactions by encapsulating and concentrating the molecules in a smaller space. This is a perfect example how unexpected lifelike behaviors can emerge out of the laws of quantum mechanics. But won't these crude divisions just go wrong and kill the cell more often than not in a hot, salty water? Well, yes, there's a good chance. However, the environment isn't a simple system. It's impure. There are other molecules floating around that can stabilize the cell walls further, like amino acids. A diverse range of these building blocks were present on early Earth and are even present in our solar system. Today, life uses 20 different amino acids to make all the cellular machinery within us, like enzymes and ion channels, as well as larger structures like muscle and hair. There is a miraculous relationship between amino acids that make up proteins and our next building blocks, nucleotides. A relationship that is important in helping us to understand how life's informational system may have emerged. The ability of life to create and store information is achieved by nucleotides, which are present today in RNA and DNA. RNA is believed to be involved in the origin of life because short chains of RNA serve another simpler purpose. They can also catalyze some chemical reactions, which perhaps kick-started life's early chemistry. Nucleotides have other functions too, and feature in several vitally important molecules like ATP and ADP, the pair of molecules that drive work in a cell, acetyl coenzyme A, and vitamin B12. In fact, every living cell today relies on what's known as the central dogma. DNA is translated to RNA, which encodes proteins. This is strong evidence that all life on Earth can be traced back to one life form, LUCA, the last universal common ancestor. The central dogma is a highly evolved system that has redundancy and error correcting built in. But the ability of RNA to encode proteins may have much simpler beginnings, one that doesn't require enzymes, one driven in part by the same physical pressures as fatty acids forming a cell-like structure, a mechanism that could have introduced information to protocells. You see, different RNA bases can encode specific amino acids. This means that a random string of RNA in early protocells could have produced a non-random string of amino acids, which could have conferred an advantage to the protocell containing it. Perhaps the amino acid stabilized the membrane, and it would have been more likely to survive and divide, potentially reproducing that information and passing it on. So now we have a great primordial soup of molecular potential. We have the thermodynamic encouragement for life, self-dividing cell walls and short RNA strands that could have encoded functional amino acids. How can we get past this primordial soup of small molecules for life to emerge? Well, we also need the one mechanism that is crucial to all theories: selection. Without selection pressures, in 14 billion years, molecular complexity wouldn't have moved much past basic molecules like these, let alone a complex enzyme, because you'd be relying on random processes with very low probabilities. Very much like shaking a bag of Lego bricks together for a few years and expecting a perfectly formed Death Star to pop out. As the size of a molecule grows, the space of possible configurations grows absurdly quickly, and the probability that even one specific molecule can be made in a useful quantity by chance falls to near zero. And that's just for one molecule, let alone a gold pocket watch. The creationists may have a point. Incredibly though, research suggests that the proposed chemical reactions on early Earth were capable of a kind of evolution way before they transitioned to life. Some chemical reaction pathways can produce molecules that catalyze the pathway itself. These are known as autocatalytic. This catalysis increases the flow of resources through one pathway, potentially away from a competing pathway, and therefore increases the first success. When these pathways loop around on themselves, they are known as autocatalytic sets. These are nascent forms of metabolism. Crucially, these metabolisms are spontaneous and can exist without the need for evolved enzymes. We have seen how the molecules present on early Earth interact and produce lifelike behaviors without the need for the highly specialized cellular control. Much of life's chemistry may indeed be spontaneous. Metabolism, chemical selection, division, information transfer, but in order for life to emerge and for all these processes to come together, we need time. But incredibly, not much time at all. The Earth formed around 4.54 billion years ago. The Moon was created 4.5 billion years ago. There were liquid oceans around 4.4 billion years ago, and the earliest life is present potentially as early as 4.3 billion years ago. For something regarded by many as unlikely, it's curious, don't you think, that almost as soon as it is given the chance, life emerges. Maybe life is inevitable. At least it was on the early Earth, because Earth has a lot of free energy and is, in effect, a giant battery. Some 4 billion years ago, our ocean was acidic and lacking in electrons, while the molten mantle just below it was alkaline and rich in electrons. A huge chemical charge imbalance that has been shown to be used to power chemical reactions that are evolving towards life. There is a consensus that somewhere on this world, where the inside of the Earth meets the outside, where the two ends of the battery meet, there was a spark of some sort. There are deep sea hydrothermal vents, gas-filled caves, hot springs, evaporating pools, and volcanic areas totally devoid of oxygen. All have all the elements that we think are required for life to emerge to harvest this free energy source. And all would have killed us if we were able to travel back in seconds. It is proposed that LUCA was a methanogen, originating at one location like these, an organism that reacted hydrogen with carbon dioxide to make methane. That's partly why a form of life evolving from scratch now is considered to be impossible because of the oxygen concentration. Add oxygen to hydrogen, and instead of life, you've got rocket fuel. We may never know for sure if a form of life existed before our central dogma ancestral line, but that's not to say life hasn't emerged elsewhere in our galaxy or even our solar system. Planets have been found nearby in our galaxy that are similar to Earth and could replicate the conditions of the early Earth. Our planet is not so special. Given the thermodynamic pressure for the emergence of life, it seems as though life on another planet is an inevitability. There is volcanic activity on moons orbiting Saturn and Jupiter, providing a similar environment beneath the surface to Earth too, which is why scientists are so interested in exploring the icy moons orbiting our nearby planets. Hydrogen-rich volcanic plumes, just like those from our deep-sea vents, have been observed erupting from the surface of Saturn's moon Enceladus. Despite the extreme speed with which life appeared to emerge on Earth, the time to go from single-celled to multi-celled was 1.5 billion years. It's clearly a hard jump in complexity to evolve communication and cooperation between cells, let alone interplanetary communication with alien life forms. So, although we haven't found signs of life elsewhere yet, absence of evidence is not evidence of absence. With all this, looking up to the stars, the way all these molecules work together, it's hard to feel alone in the universe. The early Earth seemed ideal for life to emerge, but then, even if it was less hospitable, there is always a chance. As Dr. Ian Malcolm said in Jurassic Park, life, finds a way. When life arises, it eventually becomes incredibly complex. But while complexity is often our ally, it has its drawbacks. Simple amoebas don't stress that they haven't finished that quarterly report, for example. Navigating life isn't always easy and can lead us anxious, lonely, or depressed. BetterHelp, the paid partner of today's video, is an online platform that can quickly connect you to professionals who can help you navigate that complexity. By listening to you and making informed suggestions, you may feel uncertain about therapy, but BetterHelp has undeniably improved lives. In the words of one user, "It's truly changed my life. My therapist helped me with so many issues and helped me to develop into a better person. It's a constant journey each week, but the progress has been immense." BetterHelp makes it easy for you to get started. First, go to their site, answer a few questions, and BetterHelp will match you to a professional who has years of experience helping people with struggles just like yours. Sessions are all online, via phone call, video chat, or messaging. It's the easiest possible way to start talking to a therapist. Start your journey with therapy online by scanning my QR code, clicking the link betterhelp.com/Astrum in the description, or choosing Astrum during sign up for a 10% discount on your first month. See if it works for you. Thanks for watching, and thanks to our crew of Astromnauts over at Patreon who help us make science knowledge freely available to everyone. Chasing the algorithm can be hit and miss sometimes, so your contributions help us keep making the content we love. And if you haven't already, but you want to join the Patreon, there's never been a better time to get in on the party. Just sign up with the link in the description. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.